Hi, everyone. My name is Cecilia. I'm an engineer at Taiko, and we're working on a synchronous composability builder or like a framework called Gwyneth. And the topic of my presentation today is L1, L2 interop and programmable block, and that's specifically regarding our design with what we call ultra transaction. So I gave this talk in Bangkok on this exact same day about synchronous composability. And previously, I touched on the fact that we can establish state lock. We established that block needs to be built with a shared sequencer to facilitate cross-chain call, right? And L2 to L2 interoperability can be easily achieved if everything is indeed sequenced in the same machine, right? If we have certain state law mechanism like sequencing protocol that ensure for example, execution ticket or pre-confirmation that ensure a sequencer gets the state lock of chain A and chain D, and it runs everything together within the same body, then it can sequence the transaction as it wants, right? So, and as it settles, we'll have a chain A and chain B interreacting with each other within the settlement of one L1 block. However, what about L1 to L2 interoperability? That's much more harder because given the current inclusion pre-confirmation that we currently have, if L1 and L2 settle somewhere in the middle of an L1 block, the builder has no assumption of L1 state. So it cannot build on top of L1 state. The L1 state is not locked, right? However, if we have execution pre-confirmation, which means if a builder, the most trivial case is if a builder wins PBS auction, right? You monopolize the building of the entire L1 block. So you can go back and forth between L2A and L2B and L1 transaction as you build, right? Or if you have execution pre-confirmation from the pre-confirmation protocol, that would be nice too. However, that is also more tricky to implement and is still being discussed in the sequencing community. So we don't have that neither, right? What we have so far is what's called top of the block pre-confirmation, top of the block inclusion pre-confirmation, where the validator promised that it will include your transaction at the top of the block. In that case, we can read the L1 state from the previous settled L1 block, and then we lock the state and we start building towards there. So the reads are possible, and we have one chance to write back to L1, right? So it's like read is okay, write only once. So the problem statement of my presentation today is how do we achieve L1 to L2 interoperability back and forth when you only have top of the block pre-confirmation? Yeah. The answer key that we have in Gwyneth is we indeed settle everything at the top of the block, and we perform shared settlement across chain in which we update the rolled up state, but also execute all of the cross-chain calls in one pass. And the intuition of that is when a single transaction is executed, the EVM is only instantiated once, which means there's no other unknown L1 transaction that can jump the queue that mess up your state. And also like upon the lock upon the state lock at top of the block, we kind of seize control of the entire block space over L1 and L2 within the lifespans of ultra transaction. And the bonus is that we can access transient storage, which is another EVM feature that that gives you the storage space that get wipes out after the transaction gets executed. Because normally storage space are expensive, they persist forever. However, if you have this kind of shared memory space that you can use, then you can put the cross-chain messaging in that space while you're processing ultra transaction. So another thing that comes automatically is you have atomicity, because since everything shares settled together, if any proof doesn't pass or anything reverts, the entire transaction revert. So the settlement in itself is atomic. You don't need any external observer or like a third-party coordinator to observe the settlement of any single chains. And we also kind of bring the settlement dependency and cross-chain constraint within the EVM. So if chain A, the settlement of certain transaction of chain A depends on the message passing from chain B, then everything is programmable because it's being compiled and written in the this ultra transaction. So yeah, and there's no external protocol to enforce anything. So we kind of bring this programmability into block space. And the validity of ultra transaction is being enforced by proving the building process of itself. So how do we build this fat transaction that kind of facilitate and settle everything, right? If you guys are familiar with account abstraction, that should immediately rings the bell that like AA allows the bundler to batch each user operation and kind of batch them and settle them together on chain. And that should immediately remind you of like, sounds like a rolled-up protocol where you literally are batching L2 transaction, right? And specifically how it works is that, for example, Alice has a smart contract code at her address, and the front end will build user operation as she react with the wallet and batch them and propose the operation together and call this execute function. And EIP 7702 allows for a fact that as this transaction goes out, the message.sender equals Alice herself versus the transaction.origin is the bundler. So semantically, Alice is basically saying anyone can call this code deployed at 0x my wallet and call that code on my behalf and do stuff on chain on my behalf as long as all of the validation passes. And how that inspires us is we kind of let our cross-chain apps inherit this protocol or deploy a proxy that has this code, this smart wallet code that has this like subcall or user ops functionality, where a proposer can propose cross-chain message on behalf of the cross-chain application to the L1 instances with transaction.origin equals the proposer and message.sender equals, for example, Uniswap, right? If we mandate all cross-chain application having the same address across L1 and L2, and this cross-chain application inherit the same interface, then we can facilitate cross-chain message in the fashion of account abstraction, right? And also the L2 to L1 calls will be executed in the L1 runtime. So we can basically have a Uniswap instance on L2 without any liquidity, and the proposer will like relay its call to L1 with the same address into its L1 instance that access its liquidity on L1. And also, I mean, this cross-chain call can go to other contracts as well that facilitate much more interoperability across different contracts. So this is what we do at the top of the Ultra transaction. We kind of collect all of the L2 to L1 call and program them as a subcall in the fashion of account abstraction, right? But what about L1 to L2 call? Well, I find it very useful to distinguish this notion of L1 runtime versus L2 build time, right? Because at build time, a shared sequencer has access to both DB locked at time t. While Gwyneth will allow the builder process to switch between DB at a function call level. So as we call from L2 to L1, when it touches the L1 state, the L1 part of the call is being relayed as a subcall, as user operation, while L2 state just got executed locally, and the proposer will just propose the L2 state at time t plus 1. Whereas the L1 part of the call gets executed at EVM runtime, which progresses the L1 state at st plus 1, right? But the nuance is that if we do it the other way around, a call is being proposed to L1, but building on locally, being simulated locally, which passed through, but as it gets executed in the L1 EVM, if there's a callback to L2 function, there's no way where the L1 EVM has access to L2 state. So the L1 runtime kind of need a oracle access to L2 output per function call to finish a L1 to L2 call while it's being executed in L1 runtime. And the oracle itself acts like a lookup table to pre-process information when you run the EVM. So how we like do that for L1 to L2 call is we collect all of the output from the building process and put them in an extension oracle so that L1 can access all of the information and finish the cross-chain call on the other way around. And there's another path that we also implemented that are more direct and faster, which is instead of relaying the call entirely, we kind of just collect the build time result and apply the state diff towards the end. So again, at time t, if there are like two L2 instances calling each other, incurring a diff in certain contract state, the builder will kind of just collect all of the state diff, apply it to local DB, and just propose it to L1 for DA and apply it to the L1 contract state, right? So this is what is gonna be in our blob, right? We have a bunch of transaction lists, and we also have state diffs that are incurred by each L2s calling each other. And if this diff ever touches L1, for example, a Uniswap L2 instance want to directly update a pool state in the mirror instance of its L1 contract, then we kind of just directly apply the state diff by looping through this function, right? Like for each storage slot for each contract that got updated, we just change the value directly. I mean, of course, there's like certain permission control. You have to make sure that the state diffs, only the proposer or the protocol is allowed to update the state, right? Yeah, so this is the runtime view of Ultra transaction after it's been proposed, right? You first update the extension oracle, and then you relay the L1 calls, and you apply the state diff, and then you settle the L2. And within the L2 settlement, you also make available the state diff that are being incurred by each sub L2 calling each other, right? So for data availability. And the nice thing is we can kind of use the space for L1 call to implement much more account abstraction functionality, right? If a transaction targeting L1 gets picked up by the L2 RPC, it will be processed and proposed as a user operation within the account abstraction protocol, so that this builder itself can potentially extract more MEV for its revenue. And also, the Oracle setup at the beginning of Ultra transaction functioned as a syscall that set up the runtime for the entire lifespan. So you basically have a coprocessor that processes any information after the settlement of some pre-processed information, right? This protocol has like much more extensibility and potential beyond this. And also like some realization that we have is that Ultra transaction is a rolled up proposal as much as a AA settlement. Ultra transaction implements account execution pre-confirmation of L1 transaction when it's processing all these AA user opt. Because if you think of it, upon the state lock at the beginning of the top of the block, and you have a bunch of user operation being sequenced in a certain way. That's basically execution pre-confirmation given a deterministic list of transactions, right? And a cross-chain builder is a shared sequencer, but also a pre-confirmation gateway, given the fact that it is giving pre-confirmation for these a subset of L1 user operation and L2 transactions. And this protocol apparently worked with most of the base rollup. And the validity of the whole thing is also kind of interesting. So there are two paths of proof that we can potentially take, right? We either put the entire builder process in ZK or in TE to prove the building process of Ultra transaction, or we kind of sub-proof the settlement of each L2 proposal, right? You can just run the EVM pass of how L2 subchain will settle its proposal. Like in L2A's view, you have a bunch of transaction lists which you process and you apply the state diff and input and output. And for L2B, you do the same thing. And towards the end, you constrain the validity of the input-output pair and constrain the validity of the state diff. And then you also prove the L1 settlement towards the end, that how your L1 EVM will process the whole thing. You put that in TEE or ZK, then you basically automatically have aggregation from L2 to L1. Right. And I'm going to give 2 examples to counter the argument of synchronous composability is underrated. So specifically, like the first goal is we want to migrate Hyperliquid as an app chain. Like how do we use our current construct to do that, right? As we know, Hyperliquid is a perp stack that has order books for longs and short, and a clearinghouse, and an oracle for price updates, right? We may as well implement the order book as a L2 app chain with fast pre-confirmation, and we can have the clearinghouse to calculate the funding rates and like the liquidation as L1 contract, and which also settles the roll-up state. And also for the extension oracle with validity proof, that is very important because price is very crucial for the operation of perpetual contracts, right? With an extension oracle that has validity proof, you can basically validate the price feed of how like this oracle, how the L2 update the price, right? And as a L1 app chain, you kind of also have composability to Ethereum L1's price feed from some other sources. Like for example, Chainlink or Uniswap that updates your on-chain price much more easily. And there's one more thing that I think is very important to out of the rollup, because with our L1 and L2 interop design, you can basically implement deposit as user operation that are picked up by L2 RPC, and you can also implement withdrawal as L2 to L1 subcall that are being relayed there. As I said, everything is being settled in one single transaction. So you basically have single slot deposit and withdrawal for all rollup, for the rollup that adopt this design. And the next example that I'm gonna go through is with Uniswap, right? Like, it's dubious whether Unichain will solve this fragmented liquidity issue. And we think that like may as well just keep all of your money on L1, right? So assuming Uniswap as a cross-chain app and her Gwyneth interface, you can literally have an L2 mirror instance without any liquidity, right? And the builder can just process L2 initiated swaps to L1 as user ops. And as the L2 builder sequence these swaps on L2, you kind of have the benefits of application-specific sequencing. And you can also do everything that asks will promise you can do. For example, do stacks arbitrage at the top of the block, at the top of the settlement. And also, user can borrow something like L1 to L2 flash loan, like taking the money out of L1 and do whatever you want to do on L2 and repay it within one settlement time, right? So yeah, like you can do whatever you want, but the nuances is that this L2 instance that has empty liquidity basically function as a liquidity entry point to L1. So the newer layer 2 doesn't need to do any like BD to like, onboard Uniswap or onboard your liquidity on L2. And I think that's a huge overhead in the rollup centric roadmap. Yeah. And also, how does everything comes together, right? People are kind of bearish in the adoption of shared sequencer because rollups are unlikely to give up their sequencing right? I actually agree. However, I'm bullish in this with the rise of base pre-confirmation. I think, like I mentioned before, based app chain and interoperable as-like application is the future of Ethereum apps, right? Like, it's 2025. It doesn't make sense for you to deploy yet another smart contract and have your user to tolerate 12 seconds block time, or it doesn't make sense for you to have another rolled up and reinvent the wheel with fragmented liquidity. I think the front end should just send the front end within wallet bundle. You should just send the bundle to the validator for pre-confirmation, and hopefully account abstraction will enable the more programmable gas pricing model. And hopefully, if the gateway signs contract with the validator, you can even have something like a gas subscription model for the wallet, right? And I think Gateway should collaborate with node operator for proposer commitment as a service. Specifically, that should include bundle settlement or AS or rolled up airdroppable services. And on the back end, in my view, rolled up is really a subset of self-sequencing app within its own domain. If you think about it, if application on Ethereum L1 is something that lives in Ethereum's address space, so basically roll-ups are just a subdomain, right? And a base builder will sit behind the gateway proposing to the validator who commits the bundle and propose for all of the L2 settlement altogether for L1 production. And each base builder can either sequence for different subdomain, or one subdomain can be sequenced by different builders with some sequencing protocol. For intra-cluster communication, Gwyneth kind of sits right here. That offers you the right interface for synchronous composability, where we have L2 to L2 call or L2 or L1 call that relays between each other. For inter-cluster communication, if we do have some shared sequencing standard, then it also makes sense for this gateway over here to facilitate message passing. There is like certain centralization factor or risk that we kind of need to consider, but I don't think that's the priority right now. I think like we should really work hard to have like fast airdroppable application and rolled up on Ethereum. So I will conclude my presentation by mentioning Fabric, right? And shout out to Drew over there who's taking the initiative on this, because everything that I mentioned, all those base infrastructure that we want, has been carefully put together and considered by this coalition. And I think as we stick together, we'll have the soil to build Hyperliquid or stuff like Moonshot on Ethereum and really unify the whole chain. Thank you very much.
All right, let's thank Cecilia. We have time for a question as next speaker's getting set up. Yeah?
Yes?
I really like the idea of using statistics, like applying statistics contracts,
Mm-hmm.
and using statistics, both as applied statistics and as DA at the same time.
Yeah.
But isn't it a big problem that you need to post the statistics as code data? Like you cannot use blobs to post the statistics, right? So you have a big limitation in terms of DA throughput in that case. I can see it like working maybe with an L2, like L3 is on top of an L2, like it's easy to apply statistics and you have a lot of DA throughput. With L3 on top of L2, but like if you want to apply statistics in one, like you
Right.
by code data.
Right. We're not constraining this being posted by call data. So like for the state diff that are incurring from L2 calling each other, we put them in blobs, right? But if it's to L1, yes, it has to go through call data because it has to be applied, right? And that like I think it is like a hard thing that you have to pay, because if you do want these cross-chain application, you kind of do need to pay the cost of execute something somewhere, right? You already outsource the actual execution to the layer 2, and you only have a diff on L1. If you want to save the cost of like that diff further, you kind of need to compress the diff or like and decompress the diff on L1 in smart contract. I think that's like execution cost that you have to pay again, right? So it's like a trade-off between. Yes.
So did I understand correctly that you have to be the first transaction in the queue block, right?
Yes. I mean, yeah, we have to have pre-confirmation, right? So basically, that's why I also mentioned like application-specific sequencing, because like as an AS, you kind of lock the state, and then you have more control of your sequencing, and you can make deal with the validator, be like, okay, I always want to settle my AS at this point. Or like if you lock your state, on the other hand, you don't even need the top of the block, right? If Uniswap or like whatever swap keep locking its state as it goes, and only settle at this point where the state is being touched by its own designated sequencer, that you don't really need top of the block.